Hello and welcome also from my side to the panel discussion on conquering the spectrum for 6G. My name is Andreas Rösler and I'm working as a technology manager for Rohde & Schwarz, a premium supplier of test and measurement solutions. Unfortunately, we are not able to join the panel discussion today, but I would like to thank InterDigital and Northeastern University to allow us to kick off the panel with some introductory words. So let's get to it, and let's start with looking at the spectrum landscape for 5G before we're talking about 6G. As many of you know, 5G New Radio is defined for two frequency ranges, FR1 and FR2. For 3GPP releases 15 and 16, frequency range 2 ends at 52.6 GHz. For release 17, supposed to be finished by December 2021, the upper limit for FR2 is extended to 71 GHz. This is a compromise among 3GPP's members. During the initial discussions, contributing companies proposed the support of additional frequency ranges all the way up to 275 GHz. However, none of these proposals could secure enough support within the organization. A partial reason is the current regulatory situation for these higher frequencies. Meanwhile, there are regulatory initiatives to open up spectrum beyond 95 GHz and make it more accessible for academia and industry. Based on the final report of the World Radio Conference in November 2019, the International Telecommunication Union, short ITU, puts an initial focus on spectrum between 275 and 450 GHz. Similarly, the Spectrum Horizon initiative of the Federal Communication Commissions here in the United States works to create a regulatory framework that allows the access of spectrum between 95 GHz all the way up to 3 THz via experimental licenses that last up to 10 years. The wireless industry supports these initiatives via industry alliances like the Millimeter Wave Coalition. Literature study and market research suggest that a lot of the initial research for 6G focuses on D-band and G-band frequencies. Reading some marketing material could make you believe these two bands are officially assigned a spectrum for 6G wireless communication standard. I can assure you this is not the case. They are simply in reach of the industry, low-hanging fruits if you like. However, also these frequencies provide challenges not only from a technical point of view, but also from a regulatory perspective, which is a major reason why these two bands are not yet spectrum for 6G. As an example, let's take a look at the D-band, as you find this band named very often when it comes to research for 6G. The 60 GHz of bandwidth that the D-band offers are not freely accessible. In fact, there are global radio regulations in place that prohibit any radio emissions in specific parts of the frequency band. These parts are highlighted here in red. Other parts of the frequency band are used by different applications. The table provides an overview and lists the related regulations of the ITU and the FCC. If we put it all together, then we can see there are some chunks of spectrum that could be used for wireless communication, either for fixed services such as front or backhaul, or for mobile services. In total, these are 27.2 GHz of bandwidth. However, the widest individual block offers 7.5 GHz of bandwidth. Nonetheless, the band has a high interest in early research, and Rohde & Schwarz is actively supporting this research with our innovative measurement solutions. I would like to ask my colleague Sebastian in our corporate headquarters in Munich, Germany, to give us a quick overview on our latest addition to our over-the-air test solutions.
The antenna measurement system ATS1000 has been increased in frequency and measurement capabilities over the last years so that the measurement of 5G new radio devices as well as antenna measurements up to 90 GHz can be done without modification. Today's 5G devices support various frequencies, including millimeter wave at 28 GHz, 39 GHz, or even the unlicensed 60 GHz band. However, future devices might go beyond that frequency and reach even the sub-terahertz spectrum. The ATS1000 simplifies these testing needs because no mechanical modification and no additional RF cabling is required. One of the common topics of today researchers is the D-band. The goal of this setup is to measure the amplitude and phase coherent response of an unknown DUT radiating in the frequency range of 110 to 170 GHz. Far-field quantities like directivity, gain, and realized gain are of interest, as well as the possibility to perform post-processings like near-field far-field transformations and phase center calculations. The ATS1000 consists of a conical cut positioner that allows spherical 3D scanning with an accuracy of 0.03 degrees. To measure both polarizations simultaneously, an orthomode transducer with 2 harmonic mixers is attached to the squared horn. The DUT, designed by the IMSD, consists of an elliptical lens fabricated in low-cost, low-loss plastic material with a diameter of 35 millimeters. Now we are going to perform a 3D pattern measurement with an equidistant step size of 2 degrees together with our ZNA 43. The setup of dual polarized simultaneous measurement allows us an extremely fast measurement time of 40 minutes for 61 frequencies with an optimal dynamic range of 50 dB. The fully automated antenna measurement is performed by our software AMS32. The software allows to perform the measurement as well as all post-processings that are required once the measurement is finished. After roughly 40 minutes, the measurement is finished and the data is obtained by the software. Let's now have a look onto the final measurement result. The normalized 2D cuts of the E-plane within an elevation range from -20 to +20 degree show a very good agreement, especially at the peak point with less than 0.1 dB difference. The comparison is done between the simulation data from Empire, the direct measurement, and the near-field to far-field post-processed result. Finally, looking at the measured peak directivity and realized gain as a function of frequency, excellent agreement between test data and full-wave simulations is observed as well. Maximum gain deviations are 1.3 dB at 170 GHz for bore-side radiation.
Thank you, Sebastian, for this excellent overview. We here at Rohde & Schwarz are ready to test prototypes that are targeting potential spectrum for 6G, such as the D-band. The question remains, is this really already spectrum for 6G? What kind of regulation do we need? As licensed or unlicensed frequency bands, or even shared spectrum that is accessed through cognitive devices and networks? I'm sure the panel will address these and other questions. With that, I would like to hand it back to Professor Jornet at the 6G Symposium.
Once again, welcome to everyone. My name is José Miquel Jornet. I'm a professor at Northeastern University, and today I will be the moderator for this 4th panel in this 2-day event on conquering the spectrum. Let's get started. I believe that at this point, we're all quite convinced that the way in which we consume, therefore download, but also create and share, therefore upload information is growing drastically. Not only we have more devices, but we also like faster connections. For 5G, the target is 20 gigabits per second of peak data rate. For 6G, we're looking at least 1 terabit per second. The question is, how are we going to support this? Well, we have heard a very exciting keynote earlier today, and there have been discussions of whether this would be possible at the low end of the spectrum, or maybe as in 5G, we'll have to start looking into millimeter wave. You already know that the current release of 5G NR supports all the way up to 52.6 gigahertz. And we have heard and we know that release 17, which is coming soon, it's expected to take us all the way up to 71 gigahertz. The question then is, where will 6G lay? Well, once again, we can think of the wireless communication systems that we're utilizing today, and almost, I'm not saying all, I'm saying almost all of them are effectively under, let's say, 95 gigahertz, the majority under 10 gigahertz, but let's say under 95 gigahertz. And the result of that is that, well, we do have a spectrum that it's rather occupied, maybe not in the most efficient way. And that's why after this panel, you have a panel on sharing the spectrum, but that's what it is. Of course, if what we need is more bandwidth, an immediate thought would be, why don't you jump to optical wireless communication systems, whether it's infrared or visible? And certainly that's an area of interest. But then the question is, why would someone skip this large chunk of the spectrum between, we can discuss, hundreds of gigahertz up to a few terahertz? Well, what would we get out of this spectrum? What are the opportunities if we decide to explore the terahertz frequencies? Well, we are in the context of 6G. So the first thing that comes to mind is that, okay, we're trying to create faster wireless networks, maybe personal area networks or local area networks. There are discussions on utilizing the terahertz band for wireless backhaul, maybe to provide, infrastructure to rural areas. And, I wouldn't be afraid, and again, we can discuss later on, that maybe the terahertz band is helpful for inter-satellite communications or even space networks. And you'll see why in one slide. That's all fine. But there is another big thing that you obtain when you go to these higher frequencies, which is the opportunity to do sensing. And by sensing, I do not only mean much more precise and accurate radar or localization. I also mean imaging, and I also mean spectroscopy. So as some of you know, at these frequencies, different materials, different molecules exhibit some unique electromagnetic signatures. And actually, those can be leveraged by understanding our surroundings. And for example, today, right now, as we speak, there are several satellites developed by some of our colleagues at NASA JPL orbiting the Earth with terahertz radios on top. They are not doing communications, they are doing sensing, they are characterizing the atmosphere and also listening to signals from deep space, but they are there, terahertz radios in space, in satellites right now. Of course, when we think of communications and sensing, sometimes we put them as separate, but actually they might be together. And while communications and sensing have been very well explored at lower frequencies, at terahertz frequencies, these get a new whole meaning because, as we just said, terahertz sensing is much more than just radar and localization. It's also characterization of the medium. And that's exactly what we need to do to make communications. Till this point, we don't realize, but we have always been thinking of macro applications. But actually, there are other set of applications that comes when you go to the terahertz band, which is on the nanoscale realm. Why? Well, because as you know, the terahertz frequencies are also known as the sub-millimeter wave frequencies. And why? Well, because our wavelength is less than 1 millimeter, so we can potentially make very small antennas utilized for wireless networks on chip, device-to-device communications maybe, but also more transformative applications like enabling communication between nanosensors with physical, chemical, and biological sensing capabilities. This is not science fiction. This is more than 20 and 30 years of device research that now finally we might be able to connect to the wall. And it is in this concept that, again, it's not just nano or macro, it's actually an interface of the two. And in that realm, the Internet of Nano Things, or the idea that the user, the human is not just a user, but actually a part of the network, might start to make sense as we move forward. Of course, at this point, let's be clear, there are challenges, and it's not just that everything is done. And I would like to also say, and we'll get to discuss that, there are challenges and there are also misconceptions. So what are we going to do today? Today, we're going to follow a bottom-up approach and try to answer some of the questions that have been, shown around in the last few days or in the last few months or years, and we'll try to get the answers from the experts. We'll start talking about materials, devices, and test beds. Can I get my hands on a terahertz radio today? Actually, yes, you can. How about propagation and channel modeling? Is it really that bad that we cannot go beyond few centimeters? Well, let's ask the experts. Then how do we make the most out of these devices and the properties of the channel to still be able to communicate and meet that demand of 1 terabit per second? And as you can imagine, that's not just a problem of signal processing and physical layer. It's a problem when it comes to networks too. Of course, we need to make this in a legal framework. So what happens today with policy and regulation, and what's happening with the terahertz band and beyond as we move up? And ideally, we would like to have everyone involved, including industry, so standardization will play a key role. Good news, I'm stopped. I don't need to talk anymore. Now what we're going to do is listen to the real experts in this field, people who have been working on this for 20, 30 years or even more. And let's get started. Our first panelist is Dr. Gerhard Schwentel, the COO of Virginia Diodes, or VDI, as many of you know it, the company behind, I would say, the majority of experimental terahertz platforms today. We'll then move on to Professor Thomas Körner, who is in TU Braunschweig. He's an expert in terahertz channel experimental characterization and modeling, and he's also the chair of the IEEE 802 interest group on terahertz communications. We'll then transition to Professor Sundip Rangan at NYU and also the associate director of NYU Wireless, who will try to, make us think about what needs to happen for terahertz band to transition from millimeter wave to maybe sub-terahertz band in practical applications. Then we'll go with Professor Edward Knightley from Rice University, who will show some very interesting ideas and results on how we can actually go beyond the applications of communications that we think today and talk about not just communications, but also sensing and security at these frequencies. And last but not least, Dr. Mike Marcus, formerly an FCC Senior Spectrum Policy Lead, behind many of the regulations that today are allowing this panel, including your Wi-Fi or for some of you, the millimeter wave technology, will discuss about regulation. With all this, I would like now to hand it over to Gerhard, who will be talking about the bottom of the pyramid, terahertz technology. Gerhard, please take it away.
Hi, Joseph. Thanks for having me today. I'm going to talk for a few minutes about terahertz technology challenges. I always like to start with our company's mission statement, and that's to make the terahertz region of the electromagnetic spectrum as useful for scientific, military, and commercial applications as the microwave and infrared bands are today. Next slide, please. So some of you might know us, some of you might not. I'm just going to give you a few corporate facts as an introduction. We're one of the leading millimeter wave and terahertz test and measurement companies. We also make components. We started producing mixing and multiplier diodes for radio astronomers in 1996. Today, we deliver components and test and measurement systems from 26 gigahertz to 3 terahertz. We're located in Charlottesville, Virginia with 100 employees, and we've got thousands of millimeter wave and terahertz systems in the fields. Next slide, please. So the first challenge with all of this spectrum is the amount of spectrum that's there, and that presents product and test challenges. And so generally this spectrum from 100 gigahertz to a terahertz is cut up into waveguide bands. And that does present a testing challenge for people that are engineers that have generally done at microwave type frequencies. You have to test in banded solutions, and I'm given a list of the banded solutions here. It also is makes a product challenge, as those products have to cover wide swaths of spectrum. Of particular interest these days, VDI is seeing interest at WR 6.5, 5.1, and 3.4 bands that go from 110 gigahertz to 330 gigahertz. Next slide, please. So the next challenge is the element that goes into all electronics, which is the semiconductor material. For years now, we've been successfully using CMOS and gallium arsenide in our cellular networks. All of your phones have those in them today. Gallium nitride is coming along in base station applications, both at the lower traditional cellular frequencies and millimeter wave. And those will play a part as we move up into above 100 gigahertz. But as you go farther into the terahertz region, another semiconductor material that will play a part is indium phosphide. And it's been used for a long time, but from a infrastructure and consumer commercial point of view, it is not as well developed as the other material systems. Next slide, please. So the third big technology challenge that I see is with the microelectronics architecture. So today at microwave frequencies and a little bit at millimeter wave frequencies, we use a PCB SMT type architecture. It's well suited to high volume manufacturing. And it's well established. As you move into the terahertz spectrum, the devices that are in play that have been used and produced today include integrated millimeter wave, integrated microwave assemblies, and chip and wire type architecture. These are mostly suited for low volume, high mix type applications. They generally go to higher frequency, and they're primarily in test and high-end applications. We in fact use them in our applications. being used in some electronics today is heterogeneous integration, where a somewhat combination of this chip and wire type architecture and SMT is coming together to produce things like the watches that everybody is wearing, etc. Next slide, please. So those are three of the big challenges that I see. The encouraging thing is that, as Joseph said, you can get millimeter wave radios and components today. And I've shown an example of one of those, which is a WR6.5 amplifier that VDI produces with a gain of 20 to 25 dB. It's in this integrated millimeter wave chip and wire type architecture. And it can be yours in 6 to 8 weeks. The challenges that remain for the deployment of this technology to the rest of the industry include what I mentioned previously, which is the semiconductor material. How do you develop, continue to develop GaN, indium phosphide, transitioning this microelectronics architecture from these high-end defense type applications, satellite type applications over into a commercial or consumer architecture, and then bundling that together into developing the ecosystem and supply chain that will support that. Thank you.
Excellent. Thank you very much, Gerhard. I mean, I am already seeing questions coming in, and again, very excited to see that terahertz technology might not be that far after all. Now, let's move on into our next panelist, Professor Körner, who will be talking about terahertz propagation and standardization. Professor Körner, the screen is yours.
Yeah, thank you very much, Joseph, for the introduction. I will talk mainly about terahertz propagation, but since I have been also involved quite heavily in the standardization of the first terahertz wireless system, I have also prepared one overview slide of what this standard does. So next slide, please. When talking about terahertz propagation, some people say that terahertz propagation is quite bad and hard to overcome things. So I would like to clear up a little bit about these things. There is two effects that are of interest. On the left-hand side, you see the path loss as a function of frequency. So there is a much higher path loss that we have at the UHF frequencies. This is one challenge because this means we have to overcome this high path loss by high gain antenna. And in addition to that, there is also the effect of the atmosphere and especially the weather effects like humidity or rain causes some problems for outdoor propagation. But this can be overcome. For example, if you have a backhaul link, you can reach several hundred meters if you use dish antennas with 40 to 50 dBi gain, which is possible at these frequencies. The second effect, and this is probably more interesting in indoor environments, is that you have to consider the wavelength and relate this to the size of the objects. Now you are talking about sub-millimeter wave. This means objects with sizes of a millimeter or less plays a role. And this is the case especially when it comes to reflection and scattering. So assume a rough surface like here in the middle of these three surfaces, where the surface roughness plays a role and causes additional scattering. And you probably have also multi-layer propagation. If you have, for example, a wallpaper on top of a concrete, you have multiple reflections, which then causes a different behavior in the reflection compared to the lower frequency. So next slide, I would like to give you just an example for the impact of this rough surface. So some years ago, we have done some experiments and some calculation with measuring the reflection properties with terahertz time domain spectroscopy, and we did this here in this example for a concrete plaster, which is obviously rough. And you see three curves on the right hand side, on the lower side. So there is the red curve. This is the modeling coming from Fresnel's reflection coefficients modified with the surface roughness. The blue line, this is the measurement, so it fits quite well, which is nice. But more interesting is this green line, which is a straight line. This is the reflection coefficient which you would have if there would be no roughness in the surface. And then look on the frequency on the bottom, which means that this concrete cluster is a flat surface at 100 gigahertz and becomes a rough surface, a very rough surface at about 300 to 400 gigahertz. So next slide, please. If you now look to a more realistic environment with a lot of reflection and scattering, we did some measurements in a data center, which is one of the possible application. And we used rotational units with high gain antennas in order to measure the angle of departure and angle of arrival. And what you can see on those two figures is that there is some discrete spots where you have reflections apart from the direct line of sight. So actually this situation that you need high gain antennas and that you have to find your counterpart, this will cause a challenge if we go to real mobile system, because we don't have an antenna with omnidirectional behavior. And so the device discovery and the beam tracking that you need in a mobile radio system, this is a real challenge that we have to follow. We know this already from the millimeter wave frequencies, but at terahertz, this will be even more severe. So that's the part about the propagation presentation. And now I would like to say a few words about the standards that has been developed at IEEE 802. So in 2017, the new 300 gigahertz PHY standard has been completed, and it's mainly based on a 60 gigahertz standard that takes into account already the concept of a pair net. So the assumption for this standard was that we don't have mobility, that there is no fight for access, and that there is no interference. So just two directional antennas are pointing to each other, which is possible for applications like backhaul links, links in data centers, kiosk downloading, or intra-device communication. And under this boundary condition, this first standard has been developed, and we have defined 8 different channel bandwidths between 2 gigahertz and 69 gigahertz in the frequency band 252 to 321 gigahertz. And we have defined a couple of different modulation and coding schemes to make this happen. So for sure, the work on standardization has to continue, especially to consider the effects of mobility with device discovery and beamforming. And that's the end of my talk. Thank you very much.
Thank you very much, Professor Körner. Again, I think that this presentation already cleared some of the doubts, and I'm sure we'll have more questions at the end of the panel. Now let's move on with the next panelist, Professor Rangan, who would be tell us, what are some of the key challenges we'll have to address to transition from millimeter wave to maybe sub-terahertz and eventually terahertz. So Sandeep, the screen is yours.
Okay, thanks a lot, Joseph, for giving me a chance to talk here. I have less probably to say than more just questions that to put out to the panelists. So maybe let's flip to the next slide. All right, so I just thought I would start this off on what we've learned about our first 5G millimeter wave experiences so far. So this was not my own paper, but a really good paper that came out of the University of Twin Cities last year. So maybe the results will be slightly different, when they were looking at trial data from the first deployments by Verizon in Chicago. And the bottom left of that actually shows a typical trace. And you can see those blue parts is where they're connected to the 5G millimeter wave. And you're getting rates that are close to a gigabit per second. And there are points actually elsewhere they get over gigabit per second rates. But you see that it's very, very intermittent at this point. It keeps on dropping back to 4G quite frequently without very much motion. That's obviously from a number of things. So let me flip to the next slide. And I just want to say that there's still a lot of challenges even in the millimeter wave range, and many of these are going to be exacerbated as we try to go up into the higher millimeter wave bands. So Thomas and Gerhard have spoken quite a bit about the directionality and blockage, so I won't talk about this, but allow me to talk quickly about a couple of other aspects, which are the high power consumption. On that device, actually, also the researchers found they just burnt batteries very extremely quickly on this part. And also the need to have much higher cell density. And I think another issue that a lot of the carriers have been dealing with is what are these going to be used for? So let me go to the next slide. We've been looking a little bit about the power analysis, not yet into the terahertz regime, but maybe the, let's call it the upper millimeter wave bands. And the column on the left, what was called baseline, was based on last year, there was a 6G symposium, and we tried to take a look at some state-of-the-art devices there and to try to estimate the power of what you would need. And they were coming out to be quite shocking numbers, something in the order of 6-7 watts. So that would obviously be prohibitive for any smartphone application, although it might still be possible for some other types of devices if they had more power. Now, obviously, these things can evolve. That started to make us think about how we can try to optimize different components. There had been a lot of work in the signal processing community on the ADC side. We also started looking at things like the mixers and so on. And we can push those numbers down, but they're still quite challenging numbers in about the 1 to 2 watt range. Maybe we'll see these come down and we can talk about this in the panel, but we need to be thinking about what types of applications will really merit these types of power consumption to go ahead. There also, I think, as also Gerhard mentioned, this was in BiCMOS. We're seeing a lot of activity, including with my collaborators. This was actually with UCSB in indium phosphide and other materials that will also push these power numbers down. Let's just go to, I think, to the last slide. I just wanted to talk about quickly, and maybe we'll also talk about this in the panel, on how we're going to use these devices. If the power consumption and also the desire for that data rate may not be motivated on a smartphone, we have to think of where else we're going to use this. One obvious area would be in just in point-to-point backhaul links. And I know that this has been a very good result. Actually, unfortunately, I forgot to have the reference here, but excellent paper from Ericsson in collaboration with some German universities on using line-of-sight MIMO combined with 140 gigahertz for very distant connections up to about 1.5 kilometers. And that picture on the bottom middle part there has been consistent with our own sort of ray tracing studies of that. Another possible thing is to start looking at other potential subscriber units, and those might be UAVs, which, because you can get a fairly good line of sight connection most of the time, might actually also be valuable if UAVs, it turns out, is actually a viable market. But maybe these are some of the things that we can talk about in this panel, and I'll just leave it at that.
Excellent. Thank you very much, Sundeep. Very good question, very good points. And yes, questions are coming in. So let's move now to Professor Edward Knightley, who will be talking about, the opportunities beyond communication, or new opportunities that appear with new physics. Edward.
Thank you, Josep, and thanks for inviting me to the panel. So I'd like to talk briefly about communication, sensing, and security in exactly one slide each. And the ranges of frequencies I'll be discussing are 100 gigahertz up to terahertz. So next slide. So we have seen quite a few slides on motivating scenarios. And so whether it's the high speed or security we haven't heard as much about, and new enabled applications. I wanted to show the picture on the left because we often talk about VR, AR, and can debate how much data rate it needs. But I do want to point out that all the people on the left, first of all, have wires, and also they're very dense. And so it's very important to talk not just about data rate, but put in a per square meter in there. How dense are we discussing? Because that has tremendous implications for what types of frequencies we'll be exploring and what technologies we'll use. Also with sensing, I think the UAV case is extremely interesting, not just on the communication side, but radios as we go up above 100 gigahertz. So next slide, please. So one of the things we've been asking is, what's really different as we go above 100 gigahertz? And so there really are some new communication paradigms that we can think of. And so I'm showing here an example of putting a pulse into an antenna that's called a leaky wave antenna. And the point about this picture is that that different frequencies emit at different angles. And so this is something that at above 100 gigahertz allows you to do tremendously different things. So if different frequencies emit at different angles, we can potentially beam steer by adapting the frequency. Now beam steering with one antenna. Wow, right? Forget massive MIMO arrays, phased arrays. We have one antenna and you can steer the beam. That's amazing. You can also discover the path by sending a single pulse. So in a picosecond, the receiver knows which color it's receiving and can now localize. And that again is astounding, and things that we could not do at lower frequencies. One would need array processing and all sorts of other technologies and time in order to find the direction. So new devices make things challenging. So or give new opportunities. Next slide. Also sensing. So this is a result not from my lab, but from Middleman's lab. But we've seen so much about at sub-gigahertz and millimeter wave that we can now combine communication and sensing. And as we are going up in frequency, the resolution just becomes astounding. And so this is about just what are the capabilities. And so I'm showing here a graph with millimeter scale resolution with a radar. And so if the world wants millimeter scale radar, then these higher frequencies, potentially with very simple devices, again, the leaky wave antenna, a single antenna is now doing millimeter scale localization. I'm starting to get above 100 gigahertz. So this is, again, a truly fascinating new capability. So third slide. So the last thing I'd like to mention is security. And so there is a inherent advantage with security as we go to higher frequencies, that we can potentially get more and more narrow beams. And so narrow beams can thwart eavesdroppers, those that would like to listen in on a wireless conversation. Of course, we'll have encryption. So we're talking about maybe side channel attacks, or trying to understand who's communicating with who and so on. But so now when we've got these new devices, it's a dispersive transmission. Different frequencies emit differently. And this actually hurts Eve. So meaning that Eve, the eavesdropper. So if Alice and Bob are transmitting and Eve is to one side, she's actually getting a different frequency than if she was on another side. And so this actually makes an asymmetry that we don't see in single frequency transmissions, meaning, assuming Alice and Bob are putting data on multiple frequencies, Eve can't get all of them. She might get the high ones, the low ones, but she's not going to get both. This is really interesting, very fascinating. And even if Eve puts a high gain antenna, she's not going to get those frequencies. They're simply physically not there. So the point being that we can also think of new security capabilities at these new frequencies. And so that to me is the excitement as we move up, that new communication possibilities, beam steering with one antenna, new sensing, millimeter scale, and also new security. With that, thank you.
Thank you very much, Edward. Again, really nice insight of how we can leverage physics to actually enable new applications, new functionalities that we didn't have before. Excellent. So then the last panelist for the day before we start the discussion, let's hand it over to Dr. Mike Marcus. Mike, please take it away.
Thank you. As a native Bostonian, I'm glad to be here. Can I have the next slide? Okay, if you remember nothing else I say, even if you're a pure techie, in the world of wireless technology, for better or for worse, regulations, the documents shown at the left, are just as real as the Maxwell's equations that are on the right. They can stop your design and actual practical use of the system just as much as if you mess up on the right. The difference is those regulations change over time, but they don't change instantly, whereas the Maxwell's equations at the right do not change. Next. Okay, one of the people ask me how much spectrum does 6G need or how much is available. Here I show a recent article where it talks about 6G backhaul needing 1 terabit. The big question I have that will drive a lot of this, and I hope the people present will think about in the near future and try to get us some answers, is for uses such as 1 terabit per second, how many hertz do you actually need? Is 100 megahertz enough? Is 100 gigahertz enough? Is 20 gigahertz enough? The spectrum policy wonks like me, in order to get the spectrum needed for 6G, need to have a firm number. And unfortunately, most of the numbers we see, like in this article, where they talk about gigabits rates, but not gigahertz. Spectrum policy thinks in terms of gigahertz. We need to get a better understanding of what the technical community is looking for in the gigahertz range. Next. Now, one thing that's very different at millimeter wave terahertz is shown in these charts. Let's look at VHF, UHF, SHF, and EHF. EHF is 3300 gigahertz. Nobody misses TV channel 37. In the US, if you put your spectrum analyzer in 608, 614, you'll see there's nothing there because it's a passive band. But it's insignificant because you can see in UHF, only 2% of the spectrum is tied up in passive bands. And indeed, at all of UHF, there are only 4 passive bands. But when you move up to EHF, the world is very, very different. And the passive bands there have a huge impact on practical use of the spectrum. And the R&D community has to understand that that impact is there. If you want to change it, it's going to require some attention in a timely way. Next. And what's going on here is that that satellite shown in the lower right-hand corner is a passive satellite that does wonderful things in weather prediction, and those bands are to protect that satellite. Is that the only way to, at the moment, those satellites are protected with an absolute prohibition of all emissions in those bands are indicated. Are there other ways of doing this? And the good news is that at last year's World Radio Conference, there's a request to ITUR to study whether interference-free sharing these passive bands are possible. While it might not make sense at much lower bands because of the special characteristics of millimeter terahertz bands which have been discussed, it is plausible that there could be win-win sharing, but not with off-the-shelf technology. While radio astronomy has to be protected, in reality, that's not a major problem. It will be protected, but radio astronomy in these bands is rare, but not non-existent in populated areas. Next slide. Joseph asked me to talk a little bit about the FCC's decision last year that Chairman Pott mentioned yesterday. And here is a quick summary of what the decision was. It created several unlicensed bands where you can use 40 dBm EIRP for virtually any conceivable use. If you go outside and you build a point-to-point link, you can get up to 82 dBm if the gain is greater than 51 dBi. Ofcom, the beginning of October, adopted similar but not identical. The bands are the same, but the technical decisions, technical parameters differ slightly. Also in that band, as Chairman Pai alluded to, in theory, any frequency above 95 gigahertz can get a Spectrum Horizons experimental license for 10 years, which allows you to market equipment. So if you have a whiz-bang use and want to get to market quickly, in theory, that will allow you to do that, at least for the 10-year basis. The question is, you have to demonstrate non-interference to incumbents, and realistically, the only incumbents there are the passive satellites for all practical purposes. And you have to request, if the band has only passive allocations, you need an explanation of why you need this band. No one has applied for one of these licenses yet. There are some doubts as to how fast, how well it will actually work. Next. Okay, this is what is really there at the moment. The current if you avoid the passive bands, on the left table, the yellow column tells you the maximum bandwidth you can get that avoids all those passive bands. But it could be even worse, because on the right is the maximum bandwidth you can get if you use a band which actually has fixed and mobile allocations, which is presumably what people want to do, those rules will not change until 2027 at the earliest. Next. The good news is the ITU is considering under resolution 731 shown on left and the URL shown there, changes to the EHF bands to enabling interference-free sharing. Josep and I are working on a US contribution to do this. This is sort of the area which is needed to unblock the chessboard to allow access to the spectrum. We are looking for more collaborators who are willing to work with us. NASA has some concerns which are quite valid. I think there are technical solutions. This is a valid technical problem, and I think it's a world-class technical problem. And those of you who are interested in really helping figure out win-win sharing approaches to this, we ask that you contact either Josep or me. Thank you very much.
Thank you very much, Mike. And at this point, I'll stop sharing my screen so you can get to see all of us. And let's start with some of the questions. Actually, I would just like to say that, we of course had some topics that we wanted to discuss anyway, which are very well aligned with the questions that are coming in. So let's get started. One of the very first comments that we have heard already in this symposium, but also usually when talking about terahertz, is like, well, where does the terahertz band start? What is terahertz and what is not? So maybe, Gerhard, you would like to start with this question?
Yeah, so always a topic of conversation at any millimeter wave or terahertz conference that you go to. I think one thing we can definitely just put to bed, centimeter wave, 3 to 30 gigahertz, millimeter wave, 30 gigahertz to 300 gigahertz, submillimeter wave, 300 gigahertz to 3 terahertz. When people start asking for the definition of terahertz, it gets a little muddy. We generally think of it as 0.1 to 10 terahertz. And that's kind of where we lie. There's also other places where these definitions are kind of vague. People talk about microwave frequencies. What's the definition of microwave frequencies?
Excellent, thank you. If anyone wants to add? Okay, I think we have a clear answer. Let's move to, again, something that was already slightly mentioned here, but I would like to have Professor Körner be able to elaborate. So how well and how badly do terahertz signals propagate? We're actually, there is a question explicitly asking if, are there experimental measurements showing how signals propagate at these frequencies, maybe in the presence of obstacles? So how far is the experimental component of the terahertz channel along, and what really happens and what does not?
Yeah, so we have done actually some measurements in this arena already a couple of years ago. When it comes to an obstacle, it is pretty clear what is already difficult at millimeter wave frequencies, that signals are diffracting around the obstacle. This diffraction loss is even higher at 300 gigahertz, but you are still able to have some connection even in a non-line of sight condition if you have at least one path that is able to go between the transmitter and receiver via one reflections. And a couple of groups, including us, have made measurements that the reflection loss or scattering loss for a lot of materials is not that high. In the example that I have shown you from the measurements in the data center, we have observed a very interesting effect. There was the line of sight, and then there was a reflection from 30 degrees, both from the angle of departure and angle of arrival. And then this reflected path on the metallic parts of these racks in the data center, which was only 3 dB below the direct line of sight. And this will cause another challenge if you want to have beam steering with a phased array antenna, and due to the small wavelength, it's very hard to suppress side lobes. So sometimes you have side lobes only 5 dB down. So this may cause a problem there. So I hope that this answers the question.
That's okay, very good comment. Thank you. Then, so seeing that indeed there are some challenges, related to, for example, Sundeep mentioned the problem with power consumption. We know that the technology is coming up, but the channel then at the end of the day will have some impact. It was mentioned before, like, do we really need to go to the terahertz band for communication? So what would be the thoughts of our panelists when you get answered this question? As someone who is researching at terahertz communications, what do you think is the main reason to go to the terahertz band, or why do we think that we need it for 6G, or maybe we don't, maybe we need to go to 7G? What are the thoughts of the panel on this? And anyone can start.
Mike, I think in many uses, fiber optics, a totally non-radio system, has advantages for point-to-point connectivity. But in the real world, there are places where fiber optics is impractical or uneconomical. For example, fiber optics, while cheap in hardware, it takes time to install and can be very expensive to install. And if it's not practical to put in fiber, there are places in both cellular related and non-cellular related things where point-to-point radio communications at high speeds has real advantages because of the speed and cost.
I just tag onto Mike's comments. I think technology continues to accelerate across the board. Fiber optics definitely does a lot of the backhaul type work, but the future is ours. And as we go into the next 10, 20 years, setting up links quicker could definitely be something that the above 100 gigahertz could provide. And I'll refer back to product that's been installed over the past several decades to assist with, for instance, a niche application, high frequency trading, within the New York metropolitan area, Chicago, that was done with 70, 80, 90 gigahertz radios in that time period. And so I think that this fixed point application is definitely interesting.
As I tell my friends, don't sell their Corning stock, but there's still use for millimeter wave terahertz.
One more thought on the driving applications and when we'll need terahertz. I think if we look back historically, we, the people who design wireless and networks, have really been very bad at doing these predictions. I remember in the 90s for high-speed networking, we were asking ourselves that same question: who needs a gigabit per second wired, right? And we all kept talking about telemedicine. I mean, that was just the one we would all come up with. And I think our fallacy is to try to think of one ultra ridiculously high-speed application. And I think the reality we've seen with the wired internet has been it's aggregate. It's just many people watching Netflix and that require the high speed wired infrastructure. And so I think with wireless, it's the same thing. I don't think 1 terabit app is as compelling as many users, high density, and just wanting a massive flow of information up and down and sensing. And they want both those capabilities at the same time in a small form factor. And I think that together is going to be the key driver.
Yeah, I mean, you can always go back to some classic quotes, right? The IBM quote of there's a worldwide need for about 4 computers. And, I think remember when the iPhone came out, Steve Ballmer said, who's ever going to use a phone that you've got to touch the screen on, something to that effect.
Excellent. So yeah, please, Tom.
Yeah, I'm pretty much convinced that if we provide a system that brings you a terabit per second, there will be someone who develops an application that will fill it up. This was the case in the past. It's very difficult to think about a so-called killer application. We thought about this when 3G was introduced. What is the killer application? And at that point, nobody has seen that people are using things like WhatsApp with transmitting videos and so on. And then suddenly it was there. The technology was there to provide it, and there were some clever guys to develop some applications. I'm pretty sure similar things could happen there.
Excellent. Thank you very much. Then I'm seeing an influx of questions related to what I would say physical layer, and the answer to those is going to be related once again to what the technology can do and what do we need to do as a community. So we're receiving questions about, for example, how stable are the oscillators and crystals that probably we should not use the word crystal, but how stable are the oscillators and the signals we're having? How phase noise will enter the game. Then we're also getting questions, okay, how do we get synchronized with those? So maybe first Gerhard can comment on the stability of the system, then maybe Sandeep can elaborate into how we deal with the real problems of real transceivers.
Yeah, so I think there's a question about oscillators up at hundreds of gigahertz into the terahertz frequency, and that is a challenge. It's a challenge that we've addressed at VDI for decades now. A lot of our test and measurement systems use multiplication to get up to these frequencies. And so that is a basic technological challenge that needs to be addressed. And I think it's a good one for the research community. You cannot go to Newark and buy a 100 gigahertz oscillator or 200 gigahertz oscillator. So yeah, good point.
Sandeep, in a real system, what do we do? Because we already have phase noise at millimeter wave. So what do we need to do at the physical layer?
Yeah, so from my experience, the phase noise itself is not an insurmountable problem. At least we did take some phase noise measurements, at least say at 140 gigahertz. And it wasn't insurmountable. Even just using New Radio has, for example, a number of extra reference signals to track phase noise, and that wasn't an issue. But as Gerhard said, you do have to generate those oscillators through multiplication, and that burns a lot of power. And we found, though, that on the other hand, you could actually push down the power consumption on this because there's so many other nonlinearities in the system, and also do some splitting and some other gains, which could maybe try to save some of the power. And I'm happy to talk more about that if people want. So I don't think it's the biggest problem, but it is definitely a big contributor in power as opposed to the phase noise, I would say, at least on sort of consumer devices. Excellent.
Thank you. I mean, what I can also share from my own experience is that we do have some systems actually, combining technologies from VDI and, systems from Keysight. We have systems all the way up to 1.05. So we call that true terahertz to make sure everyone is happy. And we have, we do experience phase noise, but one of the things that I would like to highlight is that, sometimes, we think that we expect the best out from the device so we can do our signal processing, or, the device folks try to give us what we have always wanted because traditionally that's what we needed. What I would like to emphasize is that, there are so many things we can do together by understanding. For example, you mentioned all these subharmonics and harmonics being generated. So there are so many things we can leverage by co-designing the signal processing and the devices that's where we get an opportunity. In relation to this, one other question we've actually seen a couple of times already is that, well, should we stick to OFDM or will we transition to some other type of physical layer? And I remember that Thomas mentioned that the standard, for example, considers two different physical layers. So what was the decision at that time? And do you have any ideas or preferences of how do we think the modulation and coding aspects should evolve as we go towards, sub-terahertz and terahertz systems?
Yeah, so when we developed the standard, we didn't took the OFDM system because we have all this problems with the phase stability, the phase noise, and went therefore for single carrier modulation schemes, which is much easier to generate nowadays. But I think with the semiconductor technology improve, an OFDM might be also possible. There we had a second family of modulation scheme, which is just a simple on-off keying. The reason why we put this is that there is also another interesting possibility of generating a terahertz system, which is resonance tunneling diode. However, there it's difficult to have a complex signal, but with on-off keying, this works quite nicely.
Thank you. Excellent. Edward, as someone who likes to leverage sometimes the physics of the system, do you think that we should probably look at, for example, the pulse-based communications that you mentioned, right? With these super broadband signals, or what else? I know that there are some work going on. So could you discuss of what do you think we could try as we go to these frequencies?
Sure. Yeah. I mean, I would say the pulse-based systems are especially compelling for sensing, because it just really gets a near instantaneous picture of so much of the propagation environment. So I think that's compelling in a very new way, especially when coupled with the new devices. I think in terms of the communication side and the data rate and the you know, what's going to be the most efficient and easiest to implement, I'll leave that to the circuits guys to decide. But certainly, I think that there's you know, to me, the question to explore is as we make those decisions for communications, how is it impacting sensing, and how might we maybe want to couple those two? There might be a design that's just a little bit worse for communications, but boy, would it be awesome for sensing. And then we might want to make that decision if it was a standard or a product, for example.
Excellent, thank you. I think that I'm hearing you well. And what I would like to emphasize is that given that we are looking into something new, we're looking at having chunks of bandwidth, contiguous bandwidth of, you know, tens of gigahertz, maybe 100 gigahertz. So there is plenty of room for waveform engineering. And within that, you know, for example, some of the waveforms that have been used for a long time in sensing, like, you know, chirp spread spectrum, things like that, maybe make sense once again when we move to this very large chunk of frequencies, particularly potentially very frequency selective. Talking about large chunks of frequencies, and Mike, there is a question that, you know, saying how much of the frequencies that are booked for not communication users are actually for radio astronomy, and how many of those bands are actually for, you know, for passive bands that are for Earth observation. So do we need to care about the difference between being Earth observation and radio astronomy, or how much are those?
Strictly speaking, the bands are reserved for both because of the ITU doesn't make a difference. But the reality is that radio astronomy exists, but it doesn't exist in a lot of places. So for example, in Eastern Massachusetts, you have to worry a little bit about use up to 140 gigahertz because of the Haystack Observatory, but that's the only thing east of the Mississippi River. So you have to protect radio astronomy, but east of the Mississippi River, at the moment, the only place that involves is Eastern Massachusetts. And you know, it is protecting radio astronomy is a lot easier for technical reasons and non-technical reasons. And frankly, millimeter wave radio astronomy is concentrated in high arid places like the outskirts of Tucson and northern Chile.
Excellent, thank you. I think that actually these are all very good points and also need to be taken into account. For example, some of you may be familiar with the concept of national radio dynamic zones and what are the requirements for those and whatnot. So I think that, you know, we will have to also discuss those as maybe we try to create some areas which are a Wild West for communications. Fine. There is a question that is also coming multiple times, and it relates to heat in different ways. On the one hand, you know, we have already seen very large power figures. And then of course, when we think of large power, we think of heat. And Gerhard, what do we should be worried? I mean, do the BDI devices get really hot? What do we need to worry about heat?
Yeah, so it's a valid concern, the heat. And I think Sundip referred to this a little bit in his presentation. You know, it definitely becomes less of an issue if you're talking about a fixed installation or something like a car, robot moving around. We certainly, in our test and measurement systems, deal with heat dissipation on a regular basis and managing that. And just kind of, I was saying in my presentation, I think as this industry ecosystem advances and there's more experience using whether it's GaN or indium phosphide, that these heat issues will slowly be resolved. I don't see that it's an instantaneous type resolution, but it's a work in progress. It's gonna, you know, we're looking at 10 years for development of this, what's termed 6G. And I think that that's a good timeline. could be even a little too aggressive.
Okay, excellent. Actually, now if we connect, with heat, there is the other big thing that comes to mind. And again, there were some comments, and not just today, but also in the previous session, which is when we go to higher frequencies, some people become uneasy because of the impact of these signals on us or on, biological tissues. So I was wondering, for example, maybe Thomas can start, if he can update us on what's the accepted understanding of the interaction of terahertz radiation with body tissues, humans or not. There are some things that are well known, like it's not ionizing, but does it mean that we don't need to be worried? And maybe that connects with heat. So Thomas, I'm sure you have gotten this question many times before. Should we be worried from the health perspective when it comes to these frequencies?
The point is, if the higher the frequency, the lower the penetration depth. So the signal doesn't go too deep into the body. And there was some project here also with the German Metrology Institute here in Braunschweig some years ago, and they did not find any specific effect that should be of concern. Still, and this is the same for the millimeter wave. It is not as explored as the lower frequencies. So for sure, it would be wise to do some more investigations in these areas. But currently, there is no indication that it is specifically dangerous to go to these higher frequencies.
Okay, thank you. If anyone wants to add, if not, for example, Mike, do you know exactly right now what are the FCC limits when it comes to radiation from the health perspective? Are there limits actually for this, or?
Yeah, it's basically 1 milliwatt per square centimeter, and you don't have. In cell phones, you have to worry about SAR, which is absorption inside the body, but above 6 gigahertz generally is no absorption inside the body. So the limit is basically a flux limit at the surface, and it's 1 milliwatt per square centimeter.
Okay, thank you.
I can just add one thing from practical experience when we did these measurements in a data center that I have shown you. Of course, the people operating that data center were very much concerned also about the issues with the limits. And we did some calculations when we will exceed the limits, and the calculation was, as long as we are not closer as 5 centimeters to the antenna, we are far away from the limits. And then I said, okay, during the measurements, I don't want to see anybody as close to the antenna as 5 centimeters. Please stay away, because we want to measure this scenario and not the people around.
Thank you. I mean, again, and thank you for sharing the experiences. What I would like to emphasize is that for the cellular community, terahertz looks like a very new field. But once again, if you look at the combined expertise in this field, of all the panelists here, this is a field that has been very well explored. My personal message, I don't think we need to just, restudy everything, because many things have already been studied over the last 20 or 30 years. One more question, and Mike, again, your comment on the need for coexistence of passive and active services has triggered some questions. So what could be some potential solutions to, coexist in those bands that have been reserved? Some people are talking, should this be a signal processing solution? Maybe it should be hardware. What are your thoughts? And then I open this to everyone on this call for this coexistence, being able to, tackle this issue.
Okay, thank you. Let me give one possibility, not necessarily the only possibility, but almost all communication systems have elevation angles that are 0 or less than 0. The need for communications at positive elevation angles, 20 degrees, 10 degrees, is unlikely. They exist, but they're very, very rare. If you live in Albuquerque, it's different, but that's a quirk of Albuquerque. Propagation from the surface of the Earth to satellite heights at millimeter waves varies tremendously with the elevation angle, and basically for angles under 5 degrees, in addition to the free space loss, there is a very large absorption loss. For pure vertical paths, the absorption loss turns out to be negligible. So part of the solution is focus on the main beam and minimize side lobes, particularly high elevation angle side lobes. So antenna designs that suppress side lobes much better than -20 dBi, which is what ITU has assumed in the past, but is not a physical limit. So we need to figure out antenna systems that have much greater high elevation, high side lobe levels, possibly in the -40 to -60 dBi range. This has been shown to be possible. For example, the radio telescope in Green Bank has much higher side lobe suppression than any other radio telescopes because of careful design. So that's the main issue is keeping your main beam low, which is easy in communication systems, and suppressing side lobes is another factor that has to be examined to see if it'll work. There may be other approaches, but those are the main approaches.
Excellent, thank you. Anyone wants to add to coexistence? If not, I'll share my thoughts. What I would like to say is that, again, for the last 20, 30, 40 years, there have been billions of dollars, euros, you pick the currency, into developing new materials, new structures with new physics. So as a communications community, it would be kind of limiting to just think that we are going to do transmitter and receivers. So for example, the concept of frequency selective surfaces could be leveraged. The concepts of metal lenses as a way to prevent radiation in ways that we don't want could be leveraged. So there are opportunities. And not only that, we have all the entire field of signal processing and communication. So every now and then someone says the physical layer is dead. No, I think that through signal processing, we can achieve many of these functionalities. We're getting towards the end, but one question, one comment that maybe we can just grab up with that is that we were talking about coexistence of passive and active services. One question that has been coming over the chat is, could we identify what we think might be that ultimate application that combines communications, sensing, imaging, or a spectroscopy all in one? And maybe Edward, as someone who actually has touched upon all of them, how do you envision, and again, I know it's a very tough question, and probably if you have it, you want to patent the answer and become rich, but do we have an idea of what might look like that ultimate application?
Yeah, I view it more, rather than one big killer app, is to view that these functionalities will now be will in the future be available on your phone, on an access point, and then we'll just have a much richer understanding of the environment around us at all times. Now, what you will do with that, I'll leave that to the app guys, because for example, you've probably seen the recent footage of drones flying around in a house, right? Well, those drones better have some really good radar in them so they don't knock over your china cabinet and so on. So as somebody who's done drones projects, I can tell you drones are very hard to navigate, and we try not to bring them indoors. But the point being that I think it's a sort of thing that I think one of my fellow panelists said it earlier in the way of, if you build it, they will come. If you've got devices that can give you millimeter resolution of everything around you in real time, and I mean in picoseconds, I think the sky's the limit for what device and applications will emerge using that functionality.
I'll just add on to that. I mean, I think that it's not drones, but it's robots that we have hundreds of millions of moving around the world today, which is automobiles. The 77 to 79 gigahertz radars are being quite successful. They're in your Teslas and many other cars these days. But having personally used that radar, there's opportunity for improvement, and having, say, a radar/comm system at 140 gigahertz that gives you just that bit more resolution, and maybe you pair a communication system bumper to bumper on that same radio, I mean, that can be very powerful.
Excellent. Thank you. So, well, we are supposed to be wrapping up, and what I would like to highlight here is that, first of all, I mean, yes, there are challenges. And as a research community, this should make it exciting for us. There are challenges and opportunities when it comes to devices and new radios. But the good news is that, yes, today you can get a terahertz communication system to some extent, actually buy it and start using it. And you would not be the first one, because once again, there are already experimental data sets showing how terahertz signals propagate in different scenarios. So maybe we don't need to propagate the message that, and I'm not necessarily referring to this symposium here, everyone is very open-minded. I'm referring to some of the articles that every now and then appear in selective media. So can we generate terahertz signals? Oh, yes, we can. Can we do it better? Sure, we will, like everything else, right? Do terahertz signals propagate? Of course they do. Just for a few centimeters? No, and much more too. So again, let's just think of what it is and what it's not. Let's stop propagating the messages that are not true, but then let's also emphasize the messages that are true. Yeah, we can generate signals, not super strong. So antenna designers, we need you. Signal processing, we need you also to make sure that the signals go where we want them and not anywhere else. Physical layer, networking, well, as you can see, we have been at the very bottom of this pyramid that we showed at the beginning, right? That does not mean that there are not many challenges when then we try to integrate this new range of frequencies into what could be the entire network. Again, terahertz communications will not just replace, we're conquering the spectrum and not dropping the path, we're integrating, we're adding. So there are opportunities, there are challenges, there are myths, we remove the myth, we keep the challenges, and we motivate for the opportunities.